All right, so it's 6:05 over on my end. I think this is a great time to get started. Again, welcome everybody to the August CDS Customer Data Science Group. My name's Adam. I'll be hosting. We have two really amazing speakers today, David and Corinne. We're gonna start with David and have Corinne follow after. For those who haven't been here before, A, welcome, but B, our setup is essentially David and Corinne will talk for about 20 minutes each and follow about 20 minutes or so. We can have about 10 minutes QA. And QA through Zoom, as we are virtual, is there's a little QA button, if you can see on your Zoom, where you can click it, type in a question, and then when it gets to the QA section, I can help David and Corinne see those questions and they can answer them. Yeah, feel free to write them down at any time during the presentation and they'll hopefully get to them after. But great, we're really excited again to have you. First, I'd like to give a shout out not only to our speakers, but to Taylor and Carolyn who helped set this up. CDS wouldn't happen without them. And I really appreciate all the work you do. And I would clap. I wish Zoom had a clap feature so everyone could hear it, but I'm sure everyone's virtually clapping for you guys. But yeah, great. So without further ado, I'd love to introduce our first speaker, David. David is the founder CEO of Activeloop, a YC-funded startup that originally started because to help him analyze large data sets in his neuroscience lab and now helps companies streamline their deep learning efforts and really simplify their ML infrastructure. He has a CS degree from UCL and is currently taking a leave of absence from his PhD in CS at Princeton to work on Activeloop. And a fun fact, he was featured in TechCrunch at 18 for his news recommendation system. Please give a warm welcome to David.
Thank you very much, Adam, for introducing, and also I'm very happy, excited to be here to give a talk. Let me share the screen and maybe give some introduction about what I've been working before. Can you see my screen?
Yes.
Looks great. So my name is Davit. I've been before doing a PhD at Princeton University, and where we were working with large-scale neuroscience data. We were taking a mouse brain and cutting into very thin slices and then imaging each slice in order to reconstruct the connectivity of the real neural networks in the mouse brain. And in order to do that, like to collect 1 millimeter cube of data, we had to store it at petabyte scale on the cloud. And to just run the computation itself, it was costing us millions of dollars on AWS. And our goal was to try to optimize those costs as much as possible down. And that's how we got started with Activeloop. The company name was before Snark AI, and we got into Y Combinator that raised our seed fund. And we have been working with our customers to basically help them to make it more efficient and scalable, the deep learning, especially in machine learning in general, data processing. And I wanted to today talk about this kind of expectations when you want to decide to become a data scientist. What is the goal and what do you want to do? And where we see is that, hey, we want to like actually train a lot of models, try to kind of have this futuristic view of having the robots doing all the stuff that we don't want to do, and they make the decisions and all this. But in reality, when we work on data, we actually become kind of data janitors, or like you can think of it like we have to go into the data, try to manage it, learn where to store it, how to clean it, how to pre-process it, and so on. And what we have found out while working with customers is that a lot of time in their machine learning lifecycle is actually spent in data preparation. So they spend a month in average. We saw that from the service itself is that in average, a company spends 1 month from collecting the data and designing the machine learning problem, from getting into annotating and then preparing and then training and deploying. And our goal here is actually is there a way we can make this process more efficient? And today in this talk, we're gonna focus on the data preparation part, and especially in this kind of the iceberg that you think of it, this stuff that nobody wants to do that. And ironically, this is very important to make sure that it's correctly done so that both your models and then the deployment itself could be very well done. And later it helps a lot to activate the loop. So basically going to the goal of having this kind of active learning in the process where all models like learn instantly and then make decisions and collect data as a reality. So there I outlined what we have seen, like there are basically 7 kind of problems with managing the data at large scale. First of all, you have to make sure that there's kind of a code dependency between the file system or the local file structure you have and the code itself. So if, let's say, you want to switch the data or you want to have another data set, you have to go and modify this part to make sure that the code itself, the Python script you're writing, can actually read the data and ingest into your training process. Another problem is actually managing the pre-processing pipelines. For structured processing, structured data processing, you have like tools like Spark, or you can have like Dask that can help you to streamline this approach and make it very efficient, but still is keeping track of which features or how you do the feature transformations, how you take an image, let's say you apply some transformation, crop it, slice it, and do it. It takes a lot of effort then to put the feature transformation pipeline into the deployment process as well. And then another problem is that, let's say you work on a data set and you did some transformations, you want to share with the team so you can be very efficient, because let's say you created a feature, then the other person can use it for their own needs, or you're working on the same model, trying testing different hypotheses. And it's very important that the data set itself that you have created is synchronized across the team. Another very important point is getting into the, let's say you want to access a specific part of the data and try to visualize or try to understand what's going behind the scenes. And just not accessing, but also being able to visualize the whole data and going from the data itself, like where it is stored, like let's say it's on the cloud, and how you can make sure that the compute itself that you are doing is near the data, so you can be very efficient both in terms of the time and the cost as well, because like transferring data is very costly, inefficient, and sometimes that you're working with really large scale data, you prefer to have the data to be near the compute itself. Sorry for the troubles here. So here are the main major points that we have seen while you work with really large scale data. So today we're gonna mostly focus on the tools that that you can use for storing, versioning, controlling how to store, where to store, and do that. And some of the tools outlined here, they just go to open source and get started. There's also another one missing here, the data version control, DVC. So there's a TensorFlow datasets that you can just plug into TensorFlow and load any dataset, and that's kind of their proprietary. They want to enhance their ecosystem for TensorFlow to be able to quickly get started on training process. There's TileDB, where you can actually, it's a kind of a database for images or data frames. You can store datasets. And there are two other libraries that have more like applications. They're not less open source and more kind of enterprise or premium features where you can manage your datasets and visualize them. And also the tool that we are kind of providing, called Hub, is the Python package that helps you to both manage the data and then visualize, as we'll see later. So the main goal here, what I've seen that we have been working with some of our customers, is that for a data scientist to just get started on working with large data, they might have to spend a day or here's 40 hours to download the data, unzip all the files, learn what's the API they're using, finally load this and stream this into training, and then start this process of actually training the process. And what we want to achieve here is that everything becomes instant with the open source package that we have been working already for a year. So for today, I want to take an example. Let's say we take a very small example, very simple and trivial, so that we show why it's beneficial to use the open source package itself. So we take this Fashion MNIST dataset. I bet all of you are familiar with. It's kind of a replica of standard MNIST dataset, just with more kind of consumer-facing images. There are 10 classes you have to classify if this is a shirt, it's a bag, a sneaker, or anything else. And the goal here is why they created this dataset is because MNIST was very simple and very trivial to work on. And that's why they thought that maybe they can come up with something else that makes the classifiers to benchmark better, besides just getting 99.999 accuracy and so on. So we take this data set, and let's say you just want to get started and train a model. And this is like, you have to write 49 lines of code to be able just to load the data and then put into your training process. And we have seen like this actually takes a lot of time, because then you have to go and check how you, how the files are stored correctly, what are the files you have to download, where you should store this data. And even it's like in a simple case where the amount of data is in megabytes, like it's not even gigabytes or terabytes, it still like takes kind of an effort to be able to load this data. And what we want to simplify here is like, can we actually make this process as like 2 lines of code, like where you don't have to spend a lot of time on writing this boilerplate code, and instead you can actually focus on training the model. So that's how we kind of came up with Hub, is that you can just pip install Hub, and then in a single line, you can see Abhinav, thanks to Abhinav actually, who uploaded the data set, you can have the patient MNIST data set like instantly accessible. And the way you treat this data set is itself, you can easily transform into a PyTorch by just calling to TensorFlow and then batching it. So later we can put into the training process. If you want to use TensorFlow instead of TensorFlow, you want to use PyTorch, then just instead of like writing to TensorFlow, you write to PyTorch, and you can still use the same capabilities in PyTorch and train a model. And then you have the simple, like your code for fitting the model itself on the data set. So the main point here is that we are like really working hard on trying to remove all this like boilerplate code that you have to write in order to start training the models and then visualize the data. And then eventually we're going to move to the deployment process as well. So I want also to run a quick demo on how we visualize the data set itself. We can click on the demo and we open our web app, which is free, and you can use it. So basically after uploading your data, you can visualize all the 70,000 images and the labels themselves inside. It's like it's facial MNIST, so it's pretty simple. We have all other tools as well. Like let's say we want to go and check CFAR. CFAR is more like colorful, let's say. But the point here is that, and those are just images for now, but we are adding unstructured, like more like large scale images, and eventually as well time series data, audio and video. And basically our goal here is to be able to visualize any type of a data set. And you can still access now Coco dataset or Waymo dataset and AFT, which is more like self-driving car data sets. And we try to make it effortless to just kickstart it on training the process. And the main goal that we are working here is what I've seen while working at Princeton in a neuroscience lab. And our lab actually was building one of the first models that beat the human in a specific task. And the specific task was doing the segmentation of the neural images. And the point here, what I saw is that if you can iterate over this loop, like going from collecting data, training, and then deploying, and then again, you can achieve like superhuman accurate models, and meaning that the model itself works better than the human is doing. And it's very important how to store this data, how to manage it, and try to like remove all this unnecessary bottlenecks from the data scientist itself so they can focus on the most important. Definitely when we wanted to become like a data scientist or machine learning engineer or deep learning researcher and so on, we don't want to struggle with data. We actually want to use the data to focus on the like this tiny part, which we call like 10%. Is like actually doing the training process and running all these various experiments, hypothesis testing, and so on. And that's why we started with Activeloop on actually solving the fundamental problem for dataset management and making it very easy to visualize the data and then share the data across the team and trying to solve all the problems as well. So this is it. I would love like if you really like the Python package, if you could star us on our open source package, that will be very helpful. Do you have any questions or anything that I can be helpful with and answer anything? Thank you very much.
Awesome. Thank you so much, David, for your presentation. Really interesting stuff. I don't know if you can see, but there is a question in the QA space. Yep. I can help read it out if you can't find it.
Yeah. So the question is, can we see a diagram of his data pipeline? Do you use MQTT, NFI, Logstash, Kafka, Elasticsearch? So Actually, we don't use any of those tools. You could connect, we can add a connector. Let's say you want to stream the data from Kafka and then store this on a S3. The main nice thing about this Python package is actually it's like serverless in a sense that all this processing is done in front of you and let's say the S3 storage behind the scenes. And this is the key, one of the key things that we can achieve. There are two things that we can achieve with the scalability here. That first of all, we leverage the object storage scalability that you can scale, like let's say you want to have a petabyte scale array and you can store this as on S3, but the Python package you load, it treats it as like a very huge array. So, and the data set, like the data management is done behind the scenes. And regarding why this is very important, because you want to remove all the bottlenecks that you might have from going from the storage itself to the memory of the machine. And using this, it enables to have like near real-time compute on the data that's stored on S3, which you can stream this to the memory of the GPU itself. And let's say train a model that can do like both like data bottleneck and or compute bottleneck compute. Like I can show the benchmarks. If you're interested, please feel free to add another message and then I can get into the benchmarking part as well. So the next question is, what are the 6 pains of dataset management? So here, actually, if you saw, I added like 6, but it's actually 7. So those are the 7 data points, the pain points that I went through. And the 7th is the kind of the trick is that you have to, as a data scientist, you have to take care of the infrastructure as well and make sure that data is local to your compute. And this speeds up a lot the processing itself. And also you want to make sure that the data is not unnecessarily not transferred over one cluster from another cluster if you're doing the all processing at scale on the cloud or on-prem device. Next question is, can we visualize structured data as well? If yes, can you show one example? For now, we don't have the support for the visualization of the structured data. And that's kind of our next step, to add not just like you can see a table and then you can just go through the whole table, but more treat it as kind of a Google Sheets. So you can, let's say you want to edit one part or you want to visualize the data. Let's say you want to take one column and then say, hey, can you plot me the graph of the distribution of this column, and be able to do that. And I think inherently what we are going here for is that you can store and visualize any type of data set. And we're gonna like soon deploy this, and that's the kind of the early stages. Feel free to contribute or add issues. Let's say if you feel that structured data visualization is a very important thing, I urge you to create a issue on our GitHub repository. And then so we can like kind of prioritize what is very important for the users. Do you have any more questions or any other?
I actually have a question. So if you go back 2 slides, I think, or no, the one where you do ds equals and you load, yeah, that one, ds equals hub.load. So what exactly is the object ds in this case? Like I know it can be turned into a TensorFlow data, but is it like saving the data locally? How do I interact with the data through the ds object?
Yeah, thanks for the good question. Here, actually, ds is a lazy object, meaning that it's a meta representation of the data set. So when you do .load, if you go to and use TensorFlow datasets, it will go and load like, let's say 40 GB dataset into your local machine. So the nice property that we allow you is that ds itself is not the object itself that contains the dataset, but it contains the references for the array itself. And then you can quickly kind of, let's say you have a data set that has images and labels, and then you want to get the 1,000 image. So what I would have brought here is that I can actually show a demo, but here, like you can access this using like images and then say, I want 1,000 image of my images, like kind of the tensor way. And you can get this data in a backward, like in a lazy mode. So basically you don't download the whole data, you only download the necessary chunk that has the 1,000 word. And this allows you to have the training loop itself, when you go and write the training loop, you can, so it's here you call .fit, but let's say you have the loop itself. So it allows you to load the data while you're doing the compute. So you don't have to have the whole data downloaded to the machine. You start doing the training process. You can actually start the training process, and then the data will get streamed from the cloud or from the storage. It could be anywhere to your local machine while you are doing the training process. And this gives you kind of a layer, caching or buffering layer to kickstart the training process fast as possible.
Awesome, thank you so much.
Thank you very much for this opportunity. I hope you liked it. And thanks also for the questions as well.
Yeah, thank you so much, David, for presenting. And everyone in the audience, if you have any questions, we'll send David's contact information. It's also right there if you want to write it down quickly, but we'll send it to you via email afterwards. We're also recording this presentation, so if you want to come back and revisit it, we'll post that to you guys as well after it. But please give a virtual round of applause for David. Thank you so much for presenting.
Thank you very much.
Awesome. So with that, I think we're going to transition to our second speaker. Her name is Corinne Powers, and Corinne is the VP of Data Science at Retina, which is a customer intelligence platform focused on customer level profitability and customer lifetime value scoring. She's a PhD from Stanford in EE under the legendary Stephen Boyd. And fun fact, she took some time off from her PhD to play blackjack full time based on her card counting strategy. You can definitely talk to her about that over a drink or two. But first, I'd love to hand the floor over to Corinne and give her a warm welcome.
Thank you, Adam. And thanks for the surprise factoid about myself. I didn't realize that was in the bio. Drawing on some personal experience there, huh? All right, so I'll start by sharing my screen. Okay, can everyone see this well? I guess no one can tell me they can, but I'll assume you can. All right, so, okay, great. So today we're gonna be talking about an infinite simulation solution for non-parametric CLV. And I expect that this does not completely parse, and that's okay. We're gonna cover all of the bits and pieces of this in today's talk. But before that, I'll share a bit more about myself. So as Adam said, I work at Retina. I've been at Retina for about 1.5 years, and I lead some of the data science efforts there. Previously, I did pursue a PhD where I did focus on research in optimization theory, machine learning, and signals processing. But since graduating, I've been focusing more on development. So I work a lot in Python, developing packages, and working in PySpark notebooks. And generally, throughout my career, I'm trying to learn that my mission has been to build frameworks to learn from messy time series data. So I've kind of touched on a few different industries by now, but currently in the customer behavior space, and that's going to be the topic of conversation for today. So we're going to talk about a topic that touches on 2 big themes today. So the first one is customer lifetime value, CLV, which also goes by the name lifetime value, LTV. For all intents and purposes, they are the same thing, but this is one large topic. And the second one is time series models. As you can imagine, if you're trying to predict purchase behavior over time, you're going to need to touch on some time series models. So what we'll do today is we'll explore what's happening when we make predictions into the future based on actions from the past. So on the right, I have these 2 subfigures, and let's look at the top one first. So what this is it's 3 customers, and the x-axis is time. So as time progresses, we might observe purchases, and the size of those purchases are represented by the size of the jumps whenever the purchase occurs. So you can think of the y-axis here as like the cumulative value that a customer may spend on a brand over time. And this dark gray line is what we have already observed, and the pink dotted line is what we intend to predict in the future. So looking at the bottom subfigure, we're actually looking at the exact same data. It's just represented in a different way. So if the top figure is showing you cumulative value, the bottom figure is showing you incremental value, showing you where and how big those individual purchases are happening. But once more, the dark gray dots indicate data that is known from records, and the pink dots are what we're predicting in the future. So to draw your attention on what we're trying to do is not just predicting what the customer level parameters will be behind the model, but really trying to drill down on what do those future predictions look like for individual customers and as a function of time. So those are kind of the two individual things, is the granularity over time and granularity over customers. So let's start with some background. I don't want to dive too deep into the background because we're actually not looking at how to estimate and fit models. Rather, today, we're going to assume that there's a magical box that learns from customer data, and it tells you things like the time between transactions. We also call that intra-transaction time, or ITT. So this black box just kind of pops this out for each customer, and it's magic, and we don't really care how they do it. But what also comes out for each customer is this average order value, as well as some sort of sense for churn propensity. And things that we actually know and don't need to estimate are the time since the last transaction, which we may refer to as recency. So the key here in this particular lifetime value model is that every customer is different. We've learned for each customer all of these things, and now we want to use these things to simulate what will happen in the future over time. So this is going to be the meat of our talk today, and to get started, let's look at how this actually works, the mechanics behind it. So this is an instance of how to run one simulation. So for one customer in one simulation, the first thing I'm going to do is I'm going to check, whether that customer is considered churned or not. And this will be a random variable. And the reason for that has to do with how we learn the model or learn these terms from the data. So that's all kind of folded under the black box of fitting the model, but it's a random event. So, every simulation you run, you might get a slightly different outcome. But for the one simulation we're running right now, let's draw that random event, determine if the customer is churned. Let's draw another random event to determine the time until the next transaction. And then we can repeat 1 and 2 until the churn happens. And we also want to track progression along the way. So we're actually going to show some illustrations of this happening to really drill down a bit deeper. But before we do that, I would like to take a step back and look at this family of models, these buy till you die models. So there is an important thing to note about buy till you die models. This is essentially that black box that magically gives us those estimated parameters on the customer level. And it does that by assuming that they're random variables and that those random variables follow a parametric distribution. So I'm going to drill down on that for a second. So here is an example of a parametric distribution that buy till you die models might assume that inter-transaction times are drawn from for one customer at a time. So let's say this is one customer, and the time between their purchases is a random event. And maybe there is a peak here, which indicates the most likely time between purchases. So this might be 4 weeks, and there could be a probability of, let's say 20% that it's 4 weeks. And then, as you move to the right, you're looking at inter-transaction times of longer periods, but the probability is also dropping. And this describes that the distribution. Now, because of the way that buy till you die models are structured, the assumption is that these are drawn from this continuous gamma distribution. But on the other hand, if you're working in a discrete signal space, so someone who's had experience with signals processing or works a lot with finite outcomes, random variables with finite outcomes, you might be working in this discrete space. And you might not have any assumptions around the shape that your distribution could take. So what's happening here on the right with this pink distribution is we've bucketed the time between transactions to, say, the week level or the day level or the hour level. It doesn't really matter. But this is an instance of customers who purchase a subscription service, but have the option to skip every now and then. So this large peak corresponds to an intertransaction time, say, of 4 weeks. And most of the time on your subscription, you don't skip. And so it's 4 weeks between your purchases with some regularity. And maybe it's a month. So sometimes it's like 5 weeks, you know, like it kind of varies. But whenever you do skip, then instead of there being 4 weeks between your purchases, there's all of a sudden there's 8. And that's what this peak is. This is the peak that says, all right, so 8 weeks happens fairly often. And 12 weeks might happen with some, you know, 5–10% probability as well. And these shapes will be different for every single customer. So what's neat is if you have a way to learn these, you can actually learn a lot about individual customer level behavior just by looking at the timing between their transactions alone. But for today, what's going to be, what we're going to do is we're going to assume that the ITTs are drawn from something on the right. And this means that we have to develop new tools to run our simulations. So that's what the rest of today's talk is going to be about. All right, so let's go back to our simulations and our talk of how we generate these future predictions. So this is just a glimpse of, you know, I guess some symbols and terms that we'll use in our simulations coming up. We've already talked about recency. We've talked about intertransaction time, and you can see here they vary, so they're not the same every time, but rather they can be drawn randomly. And here is just an instance of a purchase. This is the first one in particular. And of course, over time is the x-axis. So let's simulate one customer. So you know, this gray line and these black dots indicates records that we've already observed. And so first we check, all right, if we're going to simulate behavior into the future, is this customer considered churned? Based on how little time has elapsed, probably not. All right, so we'll draw a intertransaction time between this black dot and this pink dot, and it happens to be, you know, whatever this distance is. That's great. So indicates how long into the future until the next transaction happens. Okay, so now we repeat. Should, you know, do we think according to our learned model that the customer will churn? Nope, it looks like there's a likely chance that not much time will elapse, and we do this over and over again, and at some point the customer is randomly decided to have churned. So this is one simulation. Now, of course, when we are working with multiple customers, we're going to be doing these simulations for multiple customers, and each customer will have their own intertransaction times and churn propensities. And so each of the simulations will have to draw upon those customer level behaviors. So just kind of interpreting what's going on in these 3 separate simulations. This customer has fairly erratic time between purchases. This customer looked like they were likely to churn, and this customer is very, very regular. But at some point they churn. So now we're going to, you know, circle back to our goal and think about how we can get a better estimate of a customer's future prediction than just one simulation. So, you know, the first step is let's just do many simulations. So everything on this slide is going to be one customer. So here is one simulation of purchase behavior over time. And, you know, we're drawing from the customer who has fairly regular purchases. In fact, maybe this is another subscription type product. All right, so that's the first simulation. Let's do it again. This time, our random simulation showed that there was a skip. Let's do it one more time. Now the skip happened earlier. So here we have our 3 simulations that all capture behavior that was the same behavior that was learned from a machine learning model. It's just that that model was itself capturing and learning random variables. And so the predictions themselves are random outcomes. So, you know, for a very reliable prediction, we can run many, many more simulations. And the more simulations you run, if you take the average, the more reliable and the more trust you can put in that estimate. Okay, so this is kind of where we are, and this was where the body of knowledge kind of ended, at least to my understanding, in the COV space. And everything moving forward for the rest of this talk is going to be new ideas and exploring a new solution. So just to recap once more, what's our goal? We want to predict future spend by week, or really by any unit of time, for any customer in expectation. So this in expectation is the key. Until now, you might have to run essentially as many simulations as you could, an infinite number of simulations. Now we're going to explore a way to get an analytical solution for this expected spend as a function of time. Okay, so here's the fun part. We're going to draw on a trick from probability theory, and it involves convolution. So for any of the audience members who don't know what convolution is, you know, it's not something we can cover in this talk, but it's a very fun but like tricky operations, mathematical operation. I would highly encourage you to just explore. There are plenty of wonderful YouTube videos to point out all of the application areas of convolution. Anyone who comes from signals processing or engineering probably have been exposed to it. But here we're going to use convolution in probability, which is another fun place to use it. So here's a theorem. The theorem is if a random variable x has this probability mass function f, and another random variable y has a probability mass function g, then the PMF of the sum of the two random variables is the convolution of their PMFs. So I want this to sink in, but let's use some visuals to kind of help that sink in. So on the upper left is your typical die. You have it's an equal fair die, so all 6 sides have the same probability. This is the PMF for that particular die, and yeah, you can it's straightforward. So what happens if someone comes up to you and says, I want to know the distribution over the sum of 2 die rolls. So what you're doing is you're rolling the random variable, the die, you're rolling it again, and then you're adding the outcomes. And so instead of simulating that to generate and estimate your PMF, you can instead convolve this square PMF with itself. And when you do that, you get the figure on the lower right, which is a triangle, and it has the most likely outcome at 7. And this makes sense, I think, to most of us who have played board games or used die before. So this is a fun example. You can imagine extending this to like 10 die rolls, 1,000,000 die rolls. If you keep doing this and convolving this PMF with itself over and over again, it will converge to a Gaussian. And this is in fact the law of large numbers. The fact that if you look at the sum of independent random events, an infinite number of them, they will converge to a Gaussian distribution. So that's a fun little aside. Let's step back into the goal of today's talk. All right, so let's revisit the goal. An infinite simulation, we know what this means by now, solution for non-parametric CLV. So the non-parametric, again, means that we are making no assumptions about the distribution of ITTs. Now, the reason this is an important distinction is some nicely parameterized distributions have well-known and well-established analytical formulas for calculating expectation, and so it's not quite as tricky. But as soon as you step away and let the PMF be anything, you have to kind of start from scratch, and so that's what we're doing. Now, here's how we get our solution to work. We make one key assumption. We say that we're given this maximum prediction horizon T. And that means that we can identify some maximum number of transactions M that happen in time T. So as a quick example, if T is, let's say, a year, and we are modeling ITTs on the week level, then M would be 52. You can also draw on the actual data itself to get a sense for what is the maximum number, but there exists a number that is not too large. So at least not larger than t. So here's what we'll do. We're going to consider the outcome space of everything that can possibly happen across all of our simulations for one customer at a time. So that one customer can make 0 purchases, 1 purchase, all the way up to m purchases. So these now partition the outcome space. So that's neat. Let's look at each row separately. So we can calculate the time until 1 transaction, conditioned on recency. We can calculate the time until 2 transactions using our convolution trick. And this is where it's really neat. We can continue to do this for this number up through m. So we can use this to calculate the time until m transactions using that trick. And now all that remains is to calculate the probability of each of those separate outcomes occurring. So this is where the churn model ties in. You would have to use, you have to use properties of the particular churn model that you have fit to get these probabilities, but generally it's not that challenging to predict the probability that this customer will spend once before they churn if you already have learned everything you need to learn about the random system behind it. The final step is to combine all of these outcomes together and multiply by the average order value. So this is an example of some actual customers and taking a look at the outcome of using that convolution trick. So let's start by looking at the dotted line. In both of these are 2 separate customers, and the colors and the lines all indicate the same things across the 2 customers, but they're just different in their behaviors. So the dotted blue line is this time between transactions, just generally across all orders, assuming that all of the orders are independent from one another. So let's interpret what's going on with this first customer. It looks like every 8 weeks is, most often the time between transactions, but maybe 1 in 3 times or 1 in 4 times, it's 4 or 5 weeks between purchases. So it looks like maybe 4 weeks have already elapsed when we are trying to simulate the future spend. And so the time until the first purchase, this yellow line, is conditioned on how much time has already elapsed, 4 weeks. So it's shifted over by 4 weeks and then rescaled to have probability 1. So each of these different lines is a actual distribution, sums to 1, but you would only invoke this particular distribution, like this yellow one, if you know that the customer has 1 purchase, or at least 1 purchase. So we'd have to multiply by that probability. But we can continue on and look at, let's say, the time until 2 purchases happen. So this green line is the convolution of this dotted blue line with the yellow line, and that's what gives us this green line. And then the red line to 3 purchases is the green line convolved with the blue dotted line, and it continues on and on. And we can look at the same thing over here to the right, but what's fun about the figure on the right is it kind of resonates with our intuition. Our intuition is that even if I'm very, very certain, or at least fairly certain, right? Like 33% chance probability of 1 outcome is a fairly strong sense of certainty that outcome is going to happen. So if I'm looking out 10 weeks or so, I have a very strong sense of when that timing will happen. But as I try to predict further and further into the future, looking at the time until purchases 3 and 4, it starts to become a little bit fuzzier. You can't really pin down which week it's going to happen. That makes sense because so many small variations over time can kind of add up and add to this this entropy and this lack of precision over looking into the future. So this is an example of combining all of those outcomes we just walked through, but weighting each of them by the probability that they happen, and then taking the cumulative sum over the incremental predictions. the predictions of incremental purchases. So on the left, we have transactions, and each color line here, each line is a separate customer in this particular chart. So we're looking at roughly 30 customers. These two are very active customers. Some of them are considered churned, so no future spend. And if we look further into the future, this 0 indicates today. So this 10 is 10 weeks in the future, and so on. So if we look into the near future, we have a little bit of a sense for when those purchases will happen, but eventually everything smooths out and we can't really pin down exactly what will happen. But in expectation, this is going to be the number of transactions. And then for each customer, customers have their own separate average order value. And so when you scale by that, you get a more varied sense of where the spend and where the revenue will come from. So, kind of to circle back and tie this back to the very beginning, what we've done is we have looked at these pink dashed lines, and we've tried to estimate them to the best of our ability after having fit a machine learning model or a statistical model. And we want to just very quickly predict what they will be. And we've stacked them all together on the right for many, many customers. And we've done it. We've done it in fairly efficient time. So that concludes my talk. I'm happy to answer any more questions. Yeah.
Awesome. Thank you so much, Corinne, for presenting. There are 2 questions in the queue. Oh, one's a joke, and then we have 1 question in the QA.
Okay. So I'll read the joke later, but the first question is, what are your challenges when applying this approach to subscription-based use cases? So the challenges have kind of been tackled in this talk, at least when it comes to simulating. Now, when it comes to actually fitting a machine learning model, the biggest challenge is that the current methods don't really have approaches that handle those very generic non-parametric PMFs. There is a wealth of tools to use in the Bayesian statistics space if you're working with buy till you die. And the minute you step away from buy till you die and you drop the parametric assumptions, you kind of have to treat the ITT PMF as a vector variable. And you train, maybe a machine learning model. For instance, at Retina, we use semi-supervised machine learning models in order to learn from older customers and try to predict for newer customers. But I would say just use traditional machine learning approaches to, predict this vector variable that is the ITT PMFs. And it can be as flexible as needed. The thing is, you just want to add constraints to your machine learning model that the variable is non-negative and sums to 1, so it's actually a valid distribution. Otherwise, it could just be random numbers. Are there any other questions that I can field today? So the joke, I guess I'll go ahead and share it. The buy till you die sounds like my purchasing behavior.
But
By anonymous attendee.
Corinne, what are the, because I think the simulating idea is really interesting. What are some, you think, use cases or business applications of the simulation process in itself? Like what could a customer data scientist use that for to help inform their business?
Yeah, I mean, the simplest one I can think of that is really cool with using predictions over time is just forecasting. So if I want to try and predict how many of product X will be bought in the next 4 weeks, you could run these simulations and get a sense for not only when they will happen, but like by whom, and how far into the future will that pattern continue. Other applications include, if you look far out into the future, you can kind of get a sense for how valuable are customers relative to one another. So you can start to send rewards to customers who are regular purchasers, or send out a kind of targeted retention effort if the churn propensity is growing a bit high.
Awesome, thank you so much.
Oh, we have a few more questions now.
There's a couple, wow, there's a lot more questions in the QA, and then there's one question asked in the chat, which was before the QA.
Okay, so how about I'll handle the QA, and then Adam, can you help me find the chat one?
Yes.
Okay, so the first question, can you comment on ML implementations and performance for customers in the orders of millions? Sure, so let's see, commenting on the implementations and performance. So if we're talking about millions of customers, this is kind of the general size that we work with at our company. So there are, the more customers you can learn from, generally the better. I would say this kind of falls under the umbrella of model estimation and learning rather than simulation and prediction. That's totally fine. In fact, that's great. But under the estimation stage, if you're working with Bayesian buy till you die models, in the order of millions, usually the MCMC simulations start to bog you down. And if you don't parallelize and don't scale the computational efforts, it can take days. And that's just a kind of a well-known bottleneck of those MCMC tools. So if you instead try modeling customer behavior using machine learning, you can try to find some more computationally efficient approaches. In particular, the one that we've been focusing on is parallelizable over the customers. So that's a pretty nifty trick. But at the end of the day, it's important to find models that learn from a set of customers together. So you can get you can learn from the global patterns as well as some of the local patterns. Okay. I hope that answers your question. Next, by Seymour. In your spend estimate, it looks like you assumed a constant, yes, for average order value. Have you explored interactions between the purchase frequency as you've modeled it? So this is a great question. So in order to run the simulation that we did, we had to make one assumption that I didn't actually state, which I probably should have stated, which was that the draws are independent from one another and that they do not change over time. So, by making that very simplifying assumption, it actually doesn't matter. The variance or the order values themselves, if you look at the average, then in expectation, it's going to be the same value. Now, if you expected the order value to change over time or to be dependent or coupled with the intertransaction time itself, then it's a whole different ballgame. And you have to actually draw the orders and the order size the same time you're drawing the ITT. And in fact, they're going to be one draw with two outcomes coupled together in your two-dimensional PMF. Well, at Retina, I think we hope to get there in maybe a couple of years, a year or two. But that's certainly very interesting expansion. Thanks for the great question. Next, from John, in the graph on the last slide, there didn't seem to be any flattening of cumulative spend near the end of the graph. Does this imply that the model will not predict customers who stop purchasing very well? So in that particular instance, they didn't quite flatten out, and it's because we looked forward 52 weeks, a year into the future. And if we were to run the same simulation for 5 years into the future, which I wish I'd included that graph, but it actually does flatten out after 5 years for most of the customers. So I would conclude that for that particular data set, the customers were trained to have a little bit longer than like a 1 year lifespan, or at least their lifespan would last longer than the year after which we started making predictions. And of course, this depends on the particular data set. Oh, great. And then we have a comment from an anonymous person. It says, brilliant. Thank you. And yeah, you're welcome. I love this stuff. And glad to share new tricks. And it was a really fun one to discover.
So, Corinne, thank you for answering those questions. And I think there's one last question we'll field tonight, and it's from GC. And his or her question is, what's the minimal number of transactions necessary to apply these models in the real world?
Yeah, so this is going to depend very much on the estimation model you use. So I'll start with the buy till you die models. It's usually, you can't make reliable predictions until you have around 10 to 30,000 customers. And each of those customers has at least 3 or 4 transactions. If you don't have that much data, if you have fewer customers or less data than that, you can't really get a sense for the timing, especially if you just have one purchase. There's no timing, no inter-transaction timing from which to draw. So you're kind of stuck. On the other hand, if you use semi-supervised or some unsupervised learning methods, you can make predictions using other data about those customers in order to kind of guess what the ordering, guess what the average order value would be, to guess what the inter-transaction time would be, as well as churn. So it's really a function of how much other data you have and how many customers you have as well. Okay.
Awesome. Thank you so much.
My pleasure.
Perfect. So thank you so much, Corinne, for just speaking, but also, again, David, for talking tonight was really great. I learned a lot about data science and different ways to not only process data, but how to, take in orders data and really glean insights from it. I'd like to thank everybody who stayed in attendance and really enjoyed. I see we have another QA. Oh, it's a clapping emoji from Annie. Thank you, Annie. And I hope all of you enjoyed it and come back next month. Again, shout out to Taylor and Carolyn who helped set this up. They're the ones who find the speakers and really make this happen. And again, Corinne and David, we have recorded your presentations. We'll be sending out after. And if anyone in the audience has questions, comments afterwards, we will send their contact information as well. But thank you so much, everybody, for attending. And I hope you have a wonderful Wednesday.
Thank you.